All right. In that case, I'm super excited to introduce today's speakers, John Caris. Actually, the first time I heard about John, he was referred to as the drone guru of New England. So I was very happy to hear that Tufts recruited him to work with us full time. And he joined the Tufts Data Lab as a senior drone data scientist. And at Tufts, he's building capacity around drone technology in terms of teaching and research. And in fact, I will put another plug. I'm sure you will mention it as well, but he taught a course that he will also be teaching this fall on using drones in the environmental field. I hear somebody took it there. What did you think of their class? And you didn't have any background on drones, right? So there are still seats available. Honestly, without jokes, sorry to put you on the spot. It wasn't planned. I think this is a type of course that can set you apart when looking for internships or jobs. So I think there is a handful of seats available. So if you're looking for something to build your skill set, I think this would be a great opportunity. And today we will be hearing about the potential of drone technology in the environmental field. So you know how to showcase that, but also we will hear some of the projects that the students have been working on in the class. So without further ado, please help me welcome John.
Okay, how's the volume? This is probably for our online audience, maybe of one, so that's good. So thank you, Becca. It can only go downhill from here with that glowing review, and I will demystify that drone guru of New England pretty quickly, probably, because there's a lot of tech up here, and this is not my wheelhouse, even though I'm certified to fly drones in New England and in the lower reaches of the airspace, right? So we've got some technical support in the room, and I will reach out to them as I need to. So I would like to thank the sponsors of this lecture series, members of the Environmental Studies Department that helped with the logistics and kept me on task to put this talk together. My colleagues in research technology, some of them who are here, but mostly the students that endure my teaching and will ultimately lead this drone revolution despite any meddling or you know, mistakes that I introduce into their knowledge. I was asked to keep this talk geared towards a general audience. So if you are a drone expert or like a data analyst, spatial data analyst, this talk's not for you. But there's pizza, salad, so you can stick around for that. I will be showing some student projects, so if you do want to see those, that's worth your while. But your price of admission is just a few questions that I have for you. So who here has flown a drone? Are you counting these, Coco? You getting? Okay. All right. So I would say a quarter to a third at least. That's great. And let's keep your hands up, maybe. Do I want to do that? Yeah, keep your hands up. Flown a drone, seen a drone in flight. More, oh, almost all, maybe 70, 80%. Used it within a research context. Okay, well, still pretty. And who's skeptical of drones and not a fan? Okay. Yeah, I'm a little bit skeptical too. So even though I'm going to get excited and show you a lot of material here and seem like a real advocate, I have a lot of concerns about drone technology. And probably won't get too deeply into those, if at all, but just to kind of give you my position on the technology, I approach it with caution and risk. And I am very, I'm cautiously optimistic that it will be used appropriately by most people. Okay. That's probably a good way to say it. All right, so my goal this afternoon is to leave you with the notion that drones are revolutionizing environmental science. It's not just hyperbole, although it can, grab your attention. Also, I'm not an environmental scientist. You can probably tell by my accent that I'm a geographer. I was trained as a geographer. And despite being a geographer, I do still believe, and I think drones will be revolutionizing environmental science as well as multiple industries and other commercial sectors. Okay, it's not just environmental science. We'll touch on a few of those other sectors as we go. So I'm going to share just a small fraction of why drones are kind of leading this effort in environmental science. If you're an environmental science student, you should be learning about drone technology, especially if you're in the field sciences. And I'm going to share some stories with you from my work at Smith as well here at Tufts, and most of those stories are true. Okay, so you know about that. I do like to start each course with a little activity, and I'm just going to do a few of these here, one per table maybe. These are fortune cookies. In fact, maybe I can get some assistance, one per table. And if you, so I would like you to open up your fortune cookie. You do not have to consume it, although I think these are fairly fresh and crisp. I would like you to, I don't have a whiteboard here, so we're just going to go around the room, and I want you to read your fortune. Again, one per table in the interest of time. Read your fortune, and then at the end of that fortune, you're going to add the words "with drones." Okay? And if we have a really good winner by consensus, I will give you an hour's flight lesson if you want to, okay, on a drone. All right, so again, in the interest of time, I'm just going to move this right along. So if you'd like, oh, do I need the mic? Okay. Again, too many moving parts. Well, in fact, we will move this along even faster. If you think you have a really good fortune at your table, if you don't, if it's just like nonsense, let's skip it. Okay. So read your fortune and add "with drones."
Okay. Positivity is the currency of a rich and rewarding life with drones.
Yeah. Okay. Anyone else have a good one? Yeah, that was pretty good. We're gonna have a winner, I guarantee it. Whoa. Whoa, okay. That might be a lesson right there. Yeah, yeah. Okay. Any other really good ones? Oh, Coco has one.
Your dreams will come true with drones.
Ah, okay. Just love these. We could just do this all afternoon, right? Any other winners? Bella, did you have a good one? Okay. All right. Well, you can crowdsource that and see who gets the flight lesson. But thank you for participating in that. It's a good way to get started with drones. So as part of this start, the Environmental Studies Department asked me to share my passion of why I'm doing this and how that might be of some use to you here today. And passion's a strong word, such hard-hitting questions to begin with. I'll share an origin story with you, how I got into using drones for research and for teaching. Not what you expected, right? We started with kite photography in Belize because this predated the easy availability of drones at the time. And we wanted to capture aerial imagery. Right? And so we hung a GoPro on a kite. Does this have a pointer? Can you see where I'm pointing? Ah, okay. They hide the pointer button on the pointer. Okay. So kite, and this is a GoPro hanging on a string. It's on a Picavet system, which is a French kind of a early modern gimbal. And we would fly these from the beach. We'd fly them from boats, and we had quite a bit of fun doing it. Since it was a GoPro, we also took a lot of pictures of our feet because you're programming the camera and you're trying to get it set up correctly. Pictures of our feet, pictures of our noses. And we said, well, maybe this isn't quite the system that we had imagined. We also had, our origin stories moving into a cautionary tale. We really didn't know what we were doing. Sun glare, you can see the GoPro cameras had the fisheye lens at the time, so we had to remove that distortion if we wanted to make any sense of these images. And kites, as you know, are not that easy to control, at least the kites we were flying. So it wasn't a very stable platform. We were really at the mercy of the winds. And strong wind in Belize, but it was still something that was a challenge. But we did get some results. Okay? Here you can start to make out some of the coral mound. And skipped a slide. But this leads to the question, why were we trying to do this anyway? Why did we spend all that money to go to Belize, bring students down to fly kites? Funders don't usually like to support that type of activity. Look at these bottom images here, which are satellite images, right? How much can you discern from these images? Probably not too much. And what's this stuff? Clouds, right? So if you're doing any kind of work in the tropics, it's hard to get good, clear, detailed satellite imagery. And that was our problem when we wanted to map mangrove forests and coral reefs. And this led us to try and do kite mapping. As you can see here, I've got a nice orthomosaic of this development. The property is still for sale, by the way, if you wanted to buy here. Contrast these two, as well as looking at the coral reef here and what you see in the current satellite imagery at the time. All right, so what are some of these great characteristics about drone technology that get me excited? Many, just a fraction that we're going to go over today. I'm going to probably touch on the ones that are in bold. Spatial and temporal resolution. We have a lot of fidelity over imagery, as well as when we acquire it, the temporal resolution. So that's key. That's probably the most fundamental aspect of drone technology that I want you to take away from this talk today, as well as some pizza. Integration. We can take the data that we collect with drones and integrate this with other systems, primarily geographic information systems, to do our analysis. Okay? Integration is key. It's all easy. Perspective. Drones give us a perspective that you cannot acquire in any other way, at least affordably. Right? It's very expensive to buy a helicopter. I did price them. They're upwards of $2 million. It's also very expensive to rent a pilot to fly a helicopter or a small plane. So we can get this low near Earth surface perspective at a couple $1,000s. So obviously they're affordable. They're also non-invasive, meaning we can collect data, we can collect imagery, we can collect thermal data above near Earth surface and not do any destruction or disturbance of the landscape that we're trying to map and understand, or maybe the wildlife that we're trying to understand. There are some caveats with that. We don't fly near wildlife or disturb wildlife, particularly birds, but for the most part, we're non-invasive technology here. Autonomy. Thank goodness I don't have to fly these drones manually very often, right? Can you smell what I'm cooking here? I'm not that good with technology. Right? So, but I can program the drone to fly autonomously. And we can pre-program a mission to acquire the data, and then the tiny robot comes home, we say, good job, and we collect the data, and life is good. Okay, but just a few terms. Then we'll get to some pictures and some videos, I promise. And if I ever need to speed up, give me a high sign to speed up. So I'm not good at time. Good at space, but I'm not good at time. All right, AGL. I'm going to throw quickly define these terms, and they might be sprinkled in the rest of the talk. So AGL is simply above ground level. That's what we fly above ground level. And for those of you that have flown drones or took my class, you know that we can only fly up to 400 feet above ground level, or 121 meters. Okay. Autonomous flight or flight plan, I mentioned that. BV loss, beyond visual line of sight. This is when the drone goes beyond our eyeballs to see it. And this is a rule and a regulation that is pretty hard and fast from the FAA. I think I have a definition, the Federal Aviation Administration, that likes us to keep our drones within our line of sight. So we can respond to an emergency or see general aviation, general aircraft if we need to avoid them. There are some waivers to get beyond that. They're thinking Google, Amazon drone delivery. They're not keeping their drones in sight. Right? So that's not a hard and fast rule, but for our research purposes, generally, we try to stick to that. Digital elevation models and digital surface models. These are products that are produced from the drone imagery we capture. This will become a little more clear as we go on. But the digital surface model itself, that contains all the buildings and the vegetation and the lawn furniture and those kinds of things. Whereas a DEM, that superficial features have been kind of stripped away. It's a bare earth model, so we can use it for modeling and understanding different, maybe geomorphological processes. We're okay, a few more definitions and then pictures and video. There's our FAA. I mentioned GIS. I suspect most of you know what a GIS is or have used it to manage spatial data. GNSS, Global Navigation Satellite System. These drones, and most any drone that you'll buy today, have GNSS receivers on them. And that's more advanced than just GPS. That means we can see multiple constellations. We're getting satellite signals from GLONASS, maybe, I don't know what they're doing with their system right now in Russia. Galileo, the European Union has a satellite system very similar to GPS. But the key here, the takeaway is here, we get so much positional information from multiple constellations of satellites that our accuracy is pretty good and our positioning is very good, right? We're not reliant on just one system. GSD, this is our jam for drone pilots. What's your ground sample distance? Hey, Griffin, what's your ground sample distance on that flight? So this is really important to us. We get excited about it. Basically what this is what's our pixel size in our imagery? How detailed is our imagery? And we measure that with a term and describe it with a term called ground sample distance. See some examples of that. A smaller GSD number, 1 centimeter per pixel, means more detail than, say, 5 centimeters per pixel. Okay? Oh my gosh, I think this is the last terms. Orthomosaic. This is one of the products that we produce quite often and almost all the time. This is a two-dimensional map that has been geo-rectified and distortions have been removed, so we can use it as a map in that GIS system. So we get highly accurate imagery with map-like qualities. And it's just so easy to do now that I almost lose sight of the importance of this and the magnitude that this brings to us working with drone technology. To be able to create something like this orthomosaic, you'll see many of them, with $1,000 or less or a little bit more, when you want, where you want, that's astounding. That is revolutionary. Photogrammetry is the science of building and understanding these orthomosaics, taking measurements from them. And structure from motion is a subset of photogrammetry that's a little more of a modern process. It takes advantage of some of the advances in computer vision and machine processing. And claymation, Wallace and Gromit fans, claymation is a wonderful way to explain some of these concepts. Okay, this video will show you the drone in flight. It will lay out flight lines. It will acquire images in an overlapping fashion, which is very important to producing this orthomosaic. And then we'll show you some of the output products. And I will play this. And I'll also speed it up, because who watches videos at normal speed, right? Nobody. Lost our sound, but that's okay. Overlapping images. You can see on the right, we have our AGL above ground level, and we also have coordinate information for each image. Those are mosaicked together, processed in the computer through structure from motion. That generates a 3D model, a point cloud. This digital surface model that we mentioned before, all those superficial features. We texture that model with the image information. And with this information, we can calculate 3D volumes, generate contours, profiles. And here's our orthomosaic. And now we're going to look at our GSD, 2 centimeters per pixel. Any questions? Had a good backbeat too, yeah? Especially speed it up. Oop, we don't need this again. Okay. So, backing up just a little bit, from a collection of photographs, overlapping images, we can produce all these outputs very easily, just from visible imagery. And again, this blows my mind that we're taking two-dimensional photographs, processing them in the computer with structure through structure from motion, and rendering them into a 3D product again. And then we flatten that out and take out the distortion into a usable map-like product. I mean, a journey through space and time like that is just amazing. And we do it often, daily, weekly, in the drone class. And again, you can run this at your frequency that you need to for your particular research. This is what structure from motion is in essence. So you're basically just using any camera system. We happen to have a camera system on our drones, and you are taking multiple images with sufficient overlap to be able to reconstruct a 3D model. That was a quick video. Anyone want to watch that again? We're good? Oops, didn't mean to do that. Okay. Again, we do this in our class too, a kind of a land-based exercise where we take multiple images of different features and models, and then we process those and render those to sort of mimic what the drone's doing in the sky. Same process based on photogrammetry and really structure from motion. So in essence, what this really is, it's a process where we can use consumer-grade cameras. You can use your phone for this. It doesn't have to be a highly engineered camera like traditional aerial photography used. And photographs typically are captured mostly at nadir, Got a slide to explain that coming up, but simply that means our camera is pointed straight down, okay, as we fly these patterns. We fly maybe 80% overlap on the forward flight plan, and we fly 70% on the side flight plan, coming back on the neighboring flight line. We'll see what a flight line looks like in a minute. And this process, with enough images and enough overlap, is sufficient to capture both the camera details and the orientation, the pitch, and the pose of that camera to reconstruct a 3D model. Just a visual of ground sample distance. It's the distance between two pixel centers. Bump in my chest here. That's a terrible thing to do. Okay. And on the left, we can see we have about a 1.5 centimeter pixel, centimeters per pixel resolution, which is extraordinary. And you can see smaller GSD, higher GSD example. Okay. As a drone pilot, you can control what your GSD output will be. And usually it's your research question that drives this. We don't always try to achieve the lowest GSD or the most detail. It really depends on what we're trying to visualize on the landscape, how much battery life do we have in our drone, how many images do we need, and what's our processing time. So it's a series of trade-offs that you make, but it's really driven by your research question. If you're mapping sea cucumbers and they're 20 centimeters long, you probably need a GSD that's 1/10 that. Your pixel size needs to be 1/10 that, or a 2 centimeter pixel size to be able to discern and delineate a 20 centimeter sea cucumber. Okay. That's just a rule of thumb. Your GSD should be 1/10 of your GSD. And the GSD is just a function of our flying height, which we control, our camera sensor, how big is our camera sensor system, and the focal length of that camera. Here's a flight plan. This was laid out by Griffin for a thermal flight over the Medford campus. This is the green. And you can see when we lay out a flight plan, this is the automated part of our mission planning. We get the amount of time that this flight's going to take, 5.5 minutes. We get the area that it's going to cover, 8 hectares in this case. The number of images that are going to be collected to maintain that overlap, both 80% front and 75% side, but we can adjust that as we need to. And Griffin wanted to fly at 60 meters. And I think we adjusted that once we were in the field, we flew a little lower. But once we organize that plan, this gets uploaded to the drone, and then it will fly this autonomously for us. And we just watch. And we keep our finger on the pause button or the emergency return to home button in case something goes wrong. Just going back to a few definitions, we can also program our camera to be at a certain angle. So if we want oblique angle, that might mean we want to collect more of the facades of features and build a more robust 3D model. So if you're an archaeologist, or you're in the building construction trades, or you want to get the tree canopy in a little more detail, we might pitch our camera at a different angle, more oblique, and you can see that it's picking up sides of features. Versus typically we fly it in nadir, straight overhead, because we're generally producing maps. And this is the traditional method of capturing image information for later map output. Okay. All right, some examples. I'm doing okay on time, I think. I'm going to take this off because I keep messing with the microphone. Okay. So Hurricane Joaquin, anyone remember Hurricane Joaquin? Hit the Bahamas in 2015, in October of 2015, and essentially stalled over the Bahamas. And what drones allowed us to do at the time, I was at Smith, is we went down to the Bahamas shortly thereafter, a couple months after, to do a rapid damage assessment. So temporal, we were able to go down there pretty immediately after the storm and capture some imagery. And here you can see we've overlaid that orthomosaic into a Google Earth, which probably many of you have used. And you can start to see the level of detail that we were able to capture and assess and calculate the amount of overwash that came up onto some of their beach systems. This is in the island of San Salvador. Okay. And this was then given to the Bahamian government so they could know where they needed to focus their efforts to do cleanup, improve roadways to open up access to different parts of the island. And this was done pretty quickly, pretty rapidly with students. And it was overall a success. And it's a really good story of how you can use drone technology to improve outcomes and conditions for people after a natural disaster. Spatial resolution. Let me show you. Oh, it's a live map. Okay. This is, I ran a research project on, actually it was a drone workshop on, of all places, Hurricane Island. Who does a drone workshop on an island named Hurricane Island? I did. We didn't lose any drones or people, but it was fairly successful. But I just wanted to use this to show you some examples. Now let me use my bookmarks here. So this is also showing the integration. This is drone imagery that was brought into ArcGIS Online into a web mapping application. And I also wanted to show you just this level of detail that we're able to get if you're not yet impressed. So it requires me to do something here, church tree. Maybe I won't do the island. We'll go to the ice pond. We'll go to the quarry. And we'll get rid of that. And we'll bring up our swipe tool. And I want to look at the quarry. Okay. How's that looking there? Okay. Yeah. So here's the Google Earth imagery or Maxar imagery, whoever was the vendor that acquired it. And then here's our drone imagery. And we can even zoom in here and we can start to see, it's hard for you to see, but there's actually sunken pallets in the bottom of this quarry that we were able to find and have removed because this is the island's water source. So we're trying to clean up this water supply a little bit. So that's what we can do with high resolution imagery, just one example. Thermal mapping. So again, this was a project that was begun and motivated by Griffin here after he took the fall drone class and is a campus renewal planner. And Griffin wanted to see if we could detect leaks in the steam loop system on campus. And if I'm making any, if I'm talking out of class, let me know. And so we were able to fly our thermal drone on a very cold and nasty Thursday morning off campus and acquire thermal imagery, which is measuring that heat emissivity, that heat radiation off the Earth's surface. And it's pretty clear where the steam lines are. Obviously, that's not too hard to detect, not too revolutionary. But to a trained campus planner, they might be able to detect where those leaks are or where there's failures in the system. We might see some, bright irradiated areas there that might signal a problem that need further investigation. We were just looking at hotspots. We weren't doing, this was not calibrated imagery. We weren't measuring the actual temperature, but I think it was still useful information and Griffin's still working with that. There are other heat signatures that we might want to detect with drones. with drones. Yeah. We are engaged with Mass Audubon in a project that they have developed over the years. It's called the Bobolink Project. And this is a program where they pay farmers not to hay their fields until a certain date, after the bobolinks, this grassland bird, has finished their nesting process. So with Mass Audubon and the Tufts MCM class that I'm teaching this spring, we're going to go fly some of the fields with our thermal drone to see if we can detect heat signatures of nesting bobolinks. Okay. To give the farmers a little more intuition about what's going on in that field, and maybe it does behoove them to hold off on haying. But it becomes an economic issue. What's the value of that hay versus grassland birds? You know, then we get into the politics. But we're able to capture maybe more useful information that they can make that decision from. So I'm pretty excited about this project. Any questions? Okay. Student projects. Let me just highlight two in the interest of time. These are built into story maps, which is a really powerful storytelling narration tool from ESRI. And this was a project done by Fei Young. And she looked at piping plover habitat, and she acquired drone imagery from a project called FAIR, which is FAIR open source, FAIR accessible, interoperable, and reusable data warehouse. And she analyzed the amount of beach over successive time periods, and she could calculate the amount of erosion by drawing transect might impact piping plover nesting. Okay. So again, really taking advantage of drone technology in terms of high resolution imagery and the frequency that you can acquire that, and then integrating it with another application to understand the dynamics of that system. Pretty cool, outstanding project. Keeping with outstanding projects, this was done by Becca when she was looking at areas that could be problematic in terms of breeding grounds for mosquitoes in open mining areas that could then go on to cause malaria. This is in Australia, I believe, Australian mine. Very easy to acquire that drone imagery and see the pools of water at that time that it was acquired. You know, they might drain away. But at this moment in time, the imagery acquired showed this pooling water, and Becca was able to easily quantify the surface area that might be available for breeding mosquitoes. You can tell I'm not an environmental scientist. Breeding mosquitoes is like a term I just made up. Okay. I'm going to skip the beaver pond, but we do a lot of mapping out at the Grafton campus. And maybe I will show the integration of text prompts. So this is where drone technology is going with a lot of other kind of computer-based technologies, is we're taking advantage of machine learning and generative AI to understand what's in our imagery. Okay. So I think this might be a video. So it won't go live. There's another one. Okay, so this is on Paradise Pond at Smith Campus, where we get a lot of Canadian geese. They just love to hang out here. And this is using a software application called GeoNadir, which is where that FAIR data comes from, as well as it gives us a lot of GIS-like features to analyze our data. And here I just put in the text prompt, find geese. And it quickly totaled up 9 geese there. And then I can take those little goose shapes and save them as a shapefile, and then bring them into my GIS and do further analysis, like some kind of cluster analysis. Why do the geese always cluster here? What's going on? I don't know. Let's go find out. So I'm pretty excited about using GeoNadir more with our classes. We have a license for this. So we can invite students to use it, upload their own drone imagery, and then start to maybe do some analysis and understand something going on in the environment. I will skip the query, but basically we're able to outline that query with just a few mouse clicks. I'm going to skip the student research trip, but we can come back there if there's no questions. How about that?
One-way drones can be used to help Sea Turtle Conservancy to map areas of the coastline and identify tracks and nests.
Photogrammetry is a process of taking measurements from photographs. Similar to conventional aerial photography, drones capture overlapping images that enable us to generate very accurate image maps. Unlike traditional methods, drones can occupy lower airspace and be deployed at a frequency that supports our research. The imagery captured from drones is at a higher resolution than commercial products and temporally specific to our analysis. Once we complete the flight, we process the overlapping imagery into a single georeferenced orthomosaic, which fits into the correct geographic space. We also generate a digital surface model in 3D point cloud that enables topographic analysis and modeling. The advantage is that all of the data products are georeferenced and can be viewed and analyzed in a geographic information system. Drone technology allows diverse interests within a group to converge in a research environment.
Okay. You can see my story hasn't changed, right? That was back in 2017. I'm saying the same things. Spatial resolution, temporal resolution, orthomosaic generation. I'm like Bernie Sanders, right? Bernie Sanders is saying the same thing 30 years ago, saying it again. Yeah. I'm not Bernie, but my story's sticking to my story. On that trip, we were able to map gopher tortoise burrows. And as a discovery, I said, well, with this 3D model that we get from these images, this collection of images, maybe we can do a topographic profile and find the burrows, topographically versus just visually. I don't know, we never tested this, but it was an idea. Tortoise are also very social animals. So in this imagery here, we could probably see their pathways as they visit other burrows, right? And we could use that as a proxy to figure out which burrows have been abandoned and which ones are still active, just through that activity and those desire paths of these tortoise. Can't see that from satellite imagery. So it's kind of exciting what you can do on a few days on a barrier island. Just some examples of digital surface models. We're able to see the channel of the river, kind of cool. And then we get new discoveries sometimes in this process. This is after we drained the pond to do some dredging, and we found these tracks. Anyone, any idea what these tracks are? And I'm really interested in these tiny tracks, not these. These are the tracks of the student that had to go put ground control in the mud. These little tracks here, any idea what those might be? I'll kill the suspense. We later discovered this was a large snapping turtle that lives in the pond. And we can make out, if we were to zoom in, we can see the little tail dragging between these tracks. So drones are really used a lot for turtle tracking. We're looking at the turtle tracks, we're looking at the direction, their paths, and now with artificial intelligence, we can even tell what kind of turtle it is based on the kind of the motion or the track that they leave in the sand. Skip the gap analysis. I think I have a picture of this. We're also able to capture the drone video and merge that with telemetry. So here we're just over the beaver pond. You can see the drone moving on the right. We're tracking its path, and we've synchronized that with the video. Again, useful for storytelling and also understanding the dynamics of a particular landscape. We can just scrub this back and forth and look at the video and see where the drone was at the same time. Simple tools, but it can be used pretty effectively. Okay. This is my last slide, and then we can open up for questions, see if this works. This is a drone gimmick shot. Going very slowly. All right. I'm going to end it there and hopefully have some questions. We
questions.
can go back to fortune cookies.
I can get us started. Oh,
That was a great talk. Thank you, John. One thing that captured my interest was the idea of looking for the steam leaks on campus. Could you describe the technology used for that and then comment on whether we could also look for methane gas leaks?
Yes. So, and I might call on Griffin to help out here. So we just have a pretty standard thermal sensor on this drone. And the technology, we fly in those flight paths to generate a map, an orthomosaic of emitted thermal energy. And so it's not a methane sensor, but I think people are using drones with methane sensors, particularly even in Cambridge and Boston, I believe that's happening to detect methane leaks. This is just visual, taking that thermal part of the electromagnetic spectrum, capturing it with our sensor, and then putting it onto a map. Griffin, have you found this to be useful?
Yes.
1 second. Sorry.
Oh, sorry.
Otherwise, the people online won't hear you.
Did that help? Or yes.
Yeah.
Yes.
I think it's also important to point out that, the raw imagery that we captured needed to go through an extra layer of conversion based off of humidity, temperature, emissivity through, I don't remember what that program that you found was.
It was just an R script.
Yeah. Oh, it was through an R script. Yeah. So this image here, it does kind of give a high level kind of like information on what we're seeing. However, it needs further refinement. I'm actually using NB to do more change detection with former imagery that we took in 2021. And we're finding that we can train kind of like unit gear. We can train some models into highlighting certain areas and using their temperature range to identify where actual like leaks are and what normal state heat emissivity is for like asphalt versus grass. In that image, it looks like everything is really warm, but in reality, it's not. There are some areas that are a lot warmer than others. If you actually scroll a little bit to the right, you can even see the manhole cover of a building that's actually quite hot at times. And that's where we're using to identify where we envision certain steam leaks are. But yeah, I mean, I think it was a really useful exercise. And, like John was saying, I work at within the facilities department here. And there are a ton of use cases for drones in our work. So this is also an opportunity, and I'm glad I could be a part of it.
Yeah, and that's kind of one of the key points that, get it into a subject matter expert, and then let them do some of the interpretation and analysis. Because I'm just a geographer, right? So any other questions?
I have a follow-up. Actually, John, I was thinking about your research and this question, I think it comes well after yours, about air quality. I was wondering what kind of sensors can you put on a drone, how expensive they are, and how, what is the capacity for data collection for example, air pollution?
Yeah, John would probably know much more about that than I do. Right now, our expertise is just collecting imagery, visible imagery, near infrared imagery, multispectral imagery. I don't understand enough about the dynamics of measuring air quality with a drone, and particularly what the propellers and the prop wash is going to do to a sensor on a drone. But I can answer that in part that multiple sensors now and payloads can be mounted on drones. That's increasing exponentially. LiDAR sensors, water quality detection sensors, where a drone will dip a Petri dish into a water column, collect that. There's the snot bot, where a drone flying with a Petri dish mounted on it will fly over a whale as it exhales and collect the snot
Nice.
and then return to the boat. So it's really up to the imagination of the user in some ways, and then either developing that tech or acquiring that tech, putting it on a drone and figuring out how best to fly it in that particular environment.
Yeah, I was also thinking when I thought it was very exciting, your research with the Bobolink project, but I was also wondering how does noise, for example, interfere with nesting activity, or in general, how do you factor in drone noise or drone, like we're talking about the propellers, into sample collection?
Yeah, so that's why I'm really excited to be working with the MCM students. It's up to them to help figure out that methodology. Doing some literature search, what others have discovered in terms of noise from drones, how high do we have to fly, both to collect the thermal imagery as well as not disturb the bobolinks. There's a conference in the UK every year or every other year called Quiet Drones. It's all about the sounds and the sound that drones emit and what that impact might be on the environment. I can tell you it's much less than a leaf blower. So if anyone has heard a leaf blower,
Yes.
anyone in here, drones are much quieter, but the students are going to figure that out.
Awesome.
Yeah.
I have more questions.
Yeah, sure. And I also have drones up here that you can look at after the talk. Assume you don't have greasy fingers. You can touch and hold them. But yeah, go ahead.
How about I ask you one more question and then we let people interact with the drones?
Yeah.
Can you tell us a little bit more about the certification process? What would it take for a student after they take your class to take this a step further?
We had a student do that, Janine. She said it took her about another 10 to 12 hours of study, self-study, and she's put together a short study guide as part of that process. And she passed, and now she is a certified drone pilot, meaning she can fly drones and earn income. And there's a few other rules and privileges that you can enjoy as a certified pilot versus just a recreational pilot. We still fly under the same broad set of rules defined by the FAA, but certified gives you a little more privilege, and you can make money flying your drone by taking pictures, video, creating maps. And Janine can do that now. So another 10 hours, 10, 12 hours.